we were able to compile 4,000 observations from 227 observatories around the globe of 3i Atlas.
For decades, astronomers have scanned the skies for planets, signals, and the rare anomalies that defy every rule. Now, the James Webb Space Telescope may have found one. What began as a simple observation of 3i Atlas, the third interstellar visitor in history, has turned into something stranger, darker, and impossible to ignore.
Right now, as we speak, 3i Atlas, an enormous glowing object the size of Manhattan, is speeding toward Earth on what appears to be a planned, coordinated trajectory.
Webb has revealed a glow no comet should carry. The chilling question now is this: what really is 3i Atlas? The third interstellar visitor. 3i Atlas slipped into our world as a tiny moving speck. On July 1st, 2025, a small but sharp-eyed telescope in Rio Hurtado, Chile, caught that speck drifting across a crowded sea of stars. That telescope is part of the Asteroid Terrestrial Impact Last Alert System, better known as ATLAS, a NASA-funded skywatch run by the University of Hawaii. It is a net of 4 nimble survey eyes, 2 in Hawaii, 1 in Chile, and 1 in South Africa, scanning the sky several times each night for anything new that moves. Most nights, ATLAS finds routine space rocks. This one broke the pattern the moment the orbit math came back. Instead of curling into a neat loop around the sun like a normal comet, the path stayed open. Astronomers call that hyperbolic, which is just a way of saying the comet is not tied to our sun. It is a traveler from far beyond, dropping in once and then leaving for good. That 3i means third interstellar. Only 2 interstellar visitors had ever been confirmed before: Oumuamua in 2017 and Borisov in 2019. At discovery, 3i Atlas was incredibly faint, about magnitude 18.5, and it was far out near Jupiter's distance from the Sun. Picture a dim smudge roughly 420 million miles from the Sun and about 320 million miles from Earth, gliding along the rich star fields between Serpens Cauda and Sagittarius. That part of the sky is a messy glitter of starlight, which helps explain why nobody flagged the object sooner. Once astronomers combed through older images, they found the same faint speck in June, and even back in May. Each earlier sighting tightened the orbit and backed up the same verdict. This is a visitor, not a native. Every grain of dust and every puff of gas drifting off that dark core formed under a different star, in a different neighborhood. As for the dark heart itself, the size is still being pinned down. Early guesses from survey images suggested the solid nucleus might be as large as 11 miles across, but sharper Hubble data later cut that down to a firm ceiling of about 3.5 miles. It could in fact be far smaller, just a few hundred yards wide, hidden inside the much larger coma of gas and dust. What makes it look bigger over time is not the core growing, but the surrounding clouds swelling as sunlight drives more ices into vapor. In other words, the solid body is modest, but the atmosphere it throws off keeps expanding as it warms. Let's lock in the safety facts, because that is always the next question. 3i Atlas will not buzz Earth. The smallest gap between us is about roughly 170 million miles, which is farther than the distance from the Sun to Earth. The closest brush with the Sun, what astronomers call perihelion, comes around October 30th, 2025, at roughly 130 million miles. Even then, the comet stays outside Earth's orbit and just inside Mars's path. No danger here, only curiosity. Curiosity is why the James Webb Space Telescope moved fast. Within weeks of the discovery, on August 6th, the giant gold mirror turned toward the newcomer. For less than 20 minutes, Webb spread the comet's light into a clean infrared rainbow and read the ingredients. That quick look told a big story. The glow around the solid heart, the coma, was dominated by carbon dioxide. Water was there too, along with carbon monoxide and a faint trace of a gas called carbonyl sulfide. There was dust and even signs of water ice. The gas flow was strongest on the sun-facing side, exactly what you expect when sunlight warms surface ices, and they jump straight into gas and drag tiny dust grains along. The numbers from that first web look madder. At the time of the spectrum, the comet was still far out at about 3.32 astronomical units, around 310 million miles from the Sun. Even from that distance, the carbon dioxide signal was loud. The team worked out a mixing ratio of carbon dioxide to water of about 8:1. Compared with most comets we know from our own solar system, that is unusually high. That ratio is a count of how much of each gas is streaming off the surface each second. Stack that 8:1 value against comets at similar distances, and it sits more than 6 standard deviations off the trend. This means it was way outside the usual. That odd mix hints at two possibilities. Either this comet formed closer to a carbon dioxide freeze line in its birth disk, where carbon dioxide locks into ice more easily than water, or the surface spent a very long time out in harsh radiation that reshaped the outer layers. Either way, we are peeking into someone else's kitchen and catching a fresh whiff of how their comets are baked. Still, what caught everyone off guard wasn't the chemistry, it was the light. Are we seeing artificial lights on 3I Atlas? 3I Atlas is already one of the strangest stories in modern astronomy. On the surface, it looks like just another comet, dark core, glowing coma, drifting through space. But the buzz around it has been less about its chemistry and more about a wild idea. What if part of the light we see is not sunlight bouncing off dust, but artificial, something made at the source? This idea has turned heads because it shifts the story from ice and dust to something far bigger. Now, what do people actually mean when they use that word, artificial? The easiest way to picture artificial lights is like a beacon. Imagine something in space shining on its own, like a headlamp on a car or a lighthouse by the sea. Some people even imagine the glow working like a signal, tiny flashes or repeating beats, like the tick of a clock, so anyone watching could spot a pattern. Others picture it more like a laser, one sharp color, cutting through all the natural dust and gas, the way a bright red pointer stands out in a dark room. These are only ideas, but they're ideas that can actually be tested. There's another version too. In this one, the light isn't a signal at all. It's power. The glow could be waste heat, energy being collected, or some kind of on switch that activates as the object gets close to the sun. That's where a rumor comes in. Some people claim the comet got 40% brighter in just 2 minutes. But here's the truth. No official data backs that up. No paper, no observatory log, nothing confirmed. Then there's the wildest take, that the comet is steering itself. A little wiggle in the path gets called a course correction. The glow is described like a status light, the kind you see on your laptop or TV, showing that the machine is awake. The simpler answer is just physics. Comets often wobble because jets of gas shoot out when ice warms, acting like tiny thrusters. And right now, the math still fits the normal picture. 3I Atlas is on a single dive past the sun, and it's not coming back. If any strange push shows up that jets can't explain, it'll be logged in the official orbit updates for everyone to see. But so far, nothing like that has been found. And then comes the cloak and dagger flavor. Some posts whisper about masking or jamming, as if the object is tricking our instruments so we only see what we're allowed to see. But here's the thing. Glitches and noise show up everywhere in astronomy. For it to count as jamming, the weirdness has to line up with the target's exact position in the sky and repeat in ways that normal hiccups cannot explain. So far, no observatory has released logs of such target-dependent interference for 3I Atlas. So why do serious scientists even entertain these ideas instead of laughing them off? Because years before 3I Atlas showed up, astronomers had already laid out clean ways to test for city lights in space. The most basic test comes down to brightness versus distance. If something only shines because it bounces sunlight, it fades really fast as it moves away. The drop is steep. Every step farther makes it dimmer much quicker. But if something makes its own light, the fade is slower. It still gets dimmer with distance, but not nearly as fast. That change in slope is a clear, testable signature. All you do is track brightness over time, chart how steeply it falls, and compare it with the two options. If it matches the sunlight slope, case closed. If it matches the self-lit slope, that's a major flag. Light isn't just about how bright, it's about what colors are inside it. When Webb spread out the glow from 3I Atlas into a rainbow, the result showed the broad fingerprints of common comet gases. Carbon dioxide was loud, water was clear, carbon monoxide was there, plus a trace of carbonyl sulfide. There was dust glow, and even signs of water ice. That is exactly what you expect when sunlight hits frozen material and it vaporizes. What Webb did not see were the needle-thin spikes you'd expect from a laser or a lamp engineered to glow in one color. Another test people love to mention is the phase curve. That's just a way of tracking brightness as the viewing angle changes. Think about how the moon changes brightness. When it's full, it's bright. When it's just a sliver, it's dim. That's because it's only reflecting sunlight, and the angle decides how much we see. A normal comet works the same way. Its glow should rise and fall in a predictable pattern as the viewing angle changes. But if part of the light is coming from inside the object, the rules break. The dark side shouldn't go completely dark. Imagine looking at the moon and still seeing it shadowed, half glowing faintly, something that shouldn't happen if it's just reflecting sunlight. That's the idea scientists use when they talk about city lights on distant planets. And the same test applies here. If the night side of 3I Atlas refuses to fade the way it should, that's a major clue that something else is going on. Timing matters too. Think of it like listening for a beat in a noisy room. You tap your foot until you catch the rhythm. Astronomers do the same thing with a comet's brightness. They track how the light changes over time, looking for any repeating pulse. If a steady beat shows up and it doesn't match the comet's spin or the usual flicker from gas jets, that's something unusual. If that same beat is confirmed by different telescopes in different colors, the clue gets even stronger. And if the light pulses also sync perfectly with a radio signal, then you're not just looking at ice and dust anymore. You're staring at technology. So how does all this compare to our first two interstellar visitors? Stacking up the interstellar visitors. Let's put 3I Atlas next to the other two interstellar visitors we've actually met, and see what that lineup really tells us. The first was given the Hawaiian name Oumuamua, which means scout. It was discovered on October 19, 2017 by Robert Warwick using the Pan-STARRS telescope in Hawaii. The moment it was spotted, the orbit looked wrong. Normal comets and asteroids circle the sun in closed loops. This one was not looping. Its orbit had an eccentricity greater than 1, which meant it was flying through on a one-time path from deep space. It would not stay. It would never return. At first, people expected to see a comet tail. That is what usually happens when sunlight warms up ice on the surface. But Oumuamua stayed silent. There was no coma, no gas, no dust trail. The Very Large Telescope in Chile and the Gemini Observatory in Hawaii both imaged it and found nothing around it. The light came straight from the object itself, not from a glowing cloud, and the brightness changed wildly. Over each spin, the brightness swung by about 2.5 magnitudes, which means a factor of about 10. That told us the shape was extremely stretched out. Karen Meach and her team modeled a rotation period of about 7.3 hours, and the ratio of long side to short side had to be close to 10:1 if the brightness changes were only due to shape. The surface color was reddish, which matched many outer solar system bodies, but that was about the only normal thing about it. Everything else felt off. Then came the even stranger part. Marco Micheli and his colleagues studied its path closely and found it was drifting off course in a way that simple gravity could not explain. The natural explanation for that kind of drift is gas jets on a comet acting like little thrusters. But again, there was no coma, no visible gas, no dust. Even the Spitzer Space Telescope looked in infrared 2 months after it passed Earth and could not see it. Spitzer's non-detection set a cap on the size of Oumuamua, suggesting it was only a few hundred feet across. That is tiny in space terms. It also meant there could not have been much gas venting, at least not the usual kinds like water or carbon monoxide. So how do you get comet-like thrust without comet-like gas? That puzzle sparked a huge debate. Some people even suggested it could be an alien light sail pushed by sunlight. Others kept looking for natural answers. In 2023, Jennifer Bergner and Daryl Seligman published a paper in Nature that offered a neat solution. They suggested hydrogen gas could have been trapped in the ice by cosmic rays over millions of years. When the sun warmed it, that hydrogen could have escaped as an invisible thrust. Hydrogen is very hard to detect with normal comet instruments, so the object could vent it without showing a visible coma. On top of that, astronomers realized Oumuamua was tumbling, not just spinning smoothly. The light curve did not repeat exactly each cycle, which is what you see with a wobbling body. Small objects can keep that kind of tumble for millions of years if nothing stops it. That was our first scout. Then came the second. On August 30th, 2019, a Ukrainian amateur astronomer named Gennady Borisov spotted a fuzzy new object with a handmade telescope. Unlike Oumuamua, this one looked like a comet right away. It had a coma. It had a tail. And because of that, scientists could measure its gases directly. This was named 2I Borisov, and it turned out to be a treasure chest. For the first time ever, we had a comet from another solar system that we could study in detail. The Atacama Large Millimeter Array, or ALMA, in Chile pointed at Borisov in December 2019. It measured hydrogen cyanide at levels similar to solar system comets. But the real shock was carbon monoxide. Borisov was loaded with it. The levels were dozens of times richer than what we see in typical inner solar system comets. That much carbon monoxide meant Borisov had formed in a region of extreme cold, where even carbon monoxide could freeze solid. That is colder than -420 degrees Fahrenheit. That kind of freezer is more likely around a faint red star or way out in the outer disk of a system. The Hubble Space Telescope also followed Borisov and saw its coma brighten and even break apart in March and April 2020. Images showed signs of an outburst and possible splitting. The nucleus was fragile and probably only a few tenths of a mile across. It was breaking up under the sun's heat. ESO's Very Large Telescope even studied the dust and found it behaved like dust from comet Hale-Bopp, which passed through our skies in the 1990s and was thought to be very pristine. That suggested Borisov had not been processed much by any star before arriving here. It was a sample straight from the deep freeze. And now, in 2025, we met the third, 3I Atlas. The James Webb Space Telescope took a spectrum and saw that Atlas's coma was dominated by carbon dioxide, and this chemistry was the twist. Borisov's big signature was carbon monoxide. 3I Atlas shows heavy carbon dioxide instead. That is a very different recipe. It suggests the comet formed near a carbon dioxide snowline in its original system, where that gas could freeze. In plain words, this comet grew up in a different neighborhood than Borisov. Now let's step back and see what that lineup means for the bigger picture. Before 2017, estimates for how many interstellar objects passed through our solar system were all over the map. Some said just a few, others said many, but too faint to see. After 3 in just 8 years, the odds leaned toward them being common. We just weren't looking with the right tools. The Vera C. Rubin Observatory in Chile will change that. Starting full operation soon, Rubin will scan the sky deeply and often. A 2023 analysis suggested Rubin could find several interstellar objects each year. A 2024 follow-up argued the discovery rate might jump by an order of magnitude. That means we could go from 3 in 8 years to dozens in the next decade. With numbers like that, we can start doing real population studies. And when you have enough of them, you can start building patterns. You can measure how common dry shards like Oumuamua are compared to gas-rich comets like Borisov and Atlas. You can map out the chemistry. You can test models of how different planetary systems build their icy bodies. On top of that, missions are ready to chase them. The European Space Agency is building a spacecraft called Comet Interceptor. It is planned to launch in 2029 and will wait near the Sun-Earth L2 point until a fresh comet or interstellar visitor is spotted. Then it will fly out and intercept it, with 3 probes attacking from different angles. If the target is interstellar, it will be our first ever flyby of a piece of another star system. That is a giant leap beyond telescope data, but where are these wanderers really coming from? The strange neighborhood. Our visitors call home. The best guides we've ever had for an interstellar journey are Voyager 1 and Voyager 2. These 2 spacecraft have done something no other machines have managed. They've crossed the border of our solar system and are now sailing through the very same kind of space that sends objects like Oumuamua, Borisov, and 3I Atlas our way. Crossing the line is one thing, but what's on the other side? Think of the sun as a campfire that never goes out. From that fire, a steady wind of charged particles blows outward in every direction. That wind fills a giant teardrop-shaped bubble around us. Astronomers call this bubble the heliosphere. At the very edge of it, the solar wind finally runs out of strength and gives way to the thin gas that drifts between the stars. That fragile edge is called the heliopause. Step across it, and you've officially left the solar system and entered interstellar space. Voyager 1 reached that invisible line first on August 25, 2012. At the time, it was more than 11 billion miles from the Sun. The proof came when its instruments picked up the ring of denser, colder plasma just beyond the border. Scientists could literally hear the change. They translated the pitch of the plasma waves into a number for electron density, and that number jumped by about 20 times as the craft slipped across. 6 years later, on November 5, 2018, Voyager 2 crossed as well, also more than 11 billion miles away. Its sensors told the same story, a sudden spike in density right on the far side of the border. Together, those 2 crossings gave us the first in-person sample of the ocean our interstellar visitors come from. So what is actually out there? First, there's the interstellar breeze. Our solar system is moving through a patch of gas called the local interstellar cloud, and that gas is flowing past us at about 25 miles per hour second. That's around 56,000 miles per hour, coming from the direction of the constellation Scorpius. This is what astronomers sometimes call the interstellar wind. It is warm, thousands of degrees on the Kelvin scale, but by Earth standards it is so thin it's almost nothing, more like a ghostly fog than real air. The Voyagers and Earth-orbiting missions like NASA's IBEX helped pin down the numbers. The electron density is just a few hundredths per cubic centimeter, the temperature is somewhere between 7,000 and 10,000 Kelvin, and the whole medium is laced with a magnetic field that is only a fraction of a nanotesla strong. Put simply, it's a warm, extremely thin, magnetized gas, with the occasional dust grain drifting along. That is the ocean where interstellar objects spend most of their lives. Voyager 1 then picked up something that sounds like science fiction until you hear the explanation. Beginning in 2017, its long antennas started detecting a faint, steady hum, a narrow radio tone that slowly drifts in pitch as the plasma density changes around it. This was not a one-off burst from a solar storm. It persisted for years. That hum gave scientists their first continuous heartbeat of the plasma beyond the heliopause, showing them ripples and turbulence in the gas. Picture interstellar space as a dark ocean. Voyager 1 had gotten close enough to hear the water lapping against its hull. That hum proved we could monitor the interstellar environment in real time, not just when a shockwave from the sun plows through. So, the sea is warm, thin, and faintly humming. But where do the ships in that sea, the interstellar objects, actually come from? The short answer is, they are debris from other people's planet factories. When stars are young, they are surrounded by disks of gas and dust. Inside those disks, particles collide, stick, and grow. Pebbles become boulders. Boulders grow into mile-wide chunks, and those chunks become the raw building blocks of planets. But these disks are messy. Giant planets wander inward and outward. Small worlds smash into each other. Binary stars tug on everything around them. In all that chaos, a huge amount of solid material gets thrown out of the system entirely. Simulations show that as giant planets form and shift around, they can sling tens of Earth masses of rock and ice into interstellar space over time. If a system has two suns, the ejection becomes even more efficient because gravity does the heavy lifting. Add in close encounters between young stars and crowded clusters, and you get a recipe for trillions upon trillions of frozen worlds roaming the galaxy. When Pan-STARRS spotted Oumuamua in 2017, astronomers used the fact that we found one so quickly to estimate just how many must be out there. One analysis suggested about 0.2 objects per cubic astronomical unit. That may sound tiny, but when you spread it across the solar system's volume, it means there should be thousands of Oumuamua-sized interlopers inside Neptune's orbit at any given time, most far too faint to detect. That number is staggering. It implies that nearly every star in the galaxy has been shedding debris into space for billions of years. Not every ejection looks the same. Sometimes a giant planet drags a fragile comet close and rips it apart before throwing the pieces out. Sometimes material is launched after its surface has been baked dry, leaving behind a dark shard that looks more like rock but still hides ice inside. Researchers have suggested both of those scenarios to explain why Oumuamua looked dry while Borisov looked like a classic comet. The point is, the galaxy's debris factory has many different conveyor belts, and each one produces its own flavor of wandering body. Ejection also doesn't end when a system is young. Even old stars that are shedding mass late in life can release entire clouds of comets, sending one more wave of small bodies drifting through the galaxy. That shakeout adds to the population we are now starting to see. Now, back to the Voyagers. The heliopause turned out to be razor thin. Voyager 2 crossed it in less than a day. Just beyond it, the interstellar plasma was suddenly much denser than the solar wind inside. That sharp jump, plus the steady hum Voyager 1 has been hearing, shows that this is not a blank void, but a structured environment. So when a visitor like Borisov or 3I Atlas arrives from out there, it is not falling out of pure emptiness. It is coming from a warm, magnetized gas full of atoms and dust grains. The Voyagers don't carry cameras anymore, but their numbers give us the context to understand what these visitors went through before sunlight woke them up. Thanks for watching. Now check out the videos popping up on screen for more unbelievable stories.